Hello boys and girls, welcome to another episode of FoulkesBrau. As you're aware, we're in lockdown in South Africa, so getting components and repair parts has been rather painful because everything seems to be on back order. But we have some components that have arrived, and I thought we would carry on with part 2 of the treadmill repair on the DCMD57P board. It's one of my most watched videos. It seems to be one that's quite popular, and it seems to be a board that's giving a lot of people a lot of a headache. So I thought I'd reverse engineer a bit of it and go through with it and point out what can be wrong and what you should be looking for. So let's not waste any time. Let's get on the bench and we'll take it from there. So here we are on the bench with our DCMD57P. You can see the marking down there. That's the model number that we have of this board. What we can see is we've got our AC neutral, AC live coming in here. We have a fuse that was there. We have another fuse down there that was blown. Two rather big resistors, a bridge rectifier, a relay, a nice big cap. But this doesn't really help us much because we know over here, down there, and at the back end of this cap, down there, that is where our FET and our dual diode were blown. But what were they? Obviously over here we have another little diode of sorts, a little chip in there, and two chips here. So what I've done is I've reverse engineered all this circuitry to make a little bit of sense, because we still don't have all the faults on this board, and we'll get to it in a bit. So let me just zoom out. We'll take the board out the way, and what we'll do is we'll put this a little bit of a circuit diagram here like this. So let's just fix our focus. So what we can see is we've got live and neutral coming in, which is down here, live and neutral. It goes through a fuse, a nice big resistor R50, which is a 33k resistor, to this bridge rectifier. So what we're saying, we're going through this live and neutral, through that fuse over there that's missing down there. That was this little inline sold in ceramic fuse to the bridge rectifier. On the other side we've got two capacitors. There's a capacitor on the back end and a big bulk storage capacitor here, a 470 microfarad, this one over here, and 104k easy. What you need to think of, they work in picofarads, so it's 104,000 picofarads, or what you can really say is it's 100 nanofarad. From those capacitors we go through our FET. Our FET is on the back end of this down here. So it goes through our FET, and then we have some funny little bit of circuitry going on over here. So on the well, simply put, through the FET we go through the motor, we come back through that diode array, that common cathode diode, and back to the negative. So let's deal with this part of the circuitry first. It's actually very simple. We know our motor is an inductor. It's going to be driven with a pulse width modulation. And what is going, we know that that FET was blown and that diode was blown. Now, what is the point of these two? Well, the FET is obviously to switch this voltage in pulse width modulation fashion on to the motor. The diode is there very simply put. When the FET switches off, remember we have a magnetic field that's built up in this motor. The current doesn't want to change direction in the motor. We switch the FET off. The current wants to keep flowing, but it's got nowhere to go. The current built up in this motor, so that diode allows it to go like that until the magnetic field has collapsed. If that diode wasn't there, the voltage would spike over here and destroy that FET. So that explains a lot. Either the diode went first and that collapsed well, I suspect the diode array went first. In other words, it's a bit undersized. Overcurrent, burnt out. That would have killed the FET, because when it switches off, the motor's not running, the magnetic field's got nowhere to go here, the voltage will spike. It will go over the reverse voltage of the field effect transistor and blow it. So if we put our board here like this, we've got this fancy circuitry up here with this fancy little chip here. And that fancy circuitry up there is just these couple of resistors, that little glass diode there, and this chip down here, this A3020V. Now that 3020 is an optocoupled IGBT, insulated gate bipolar junction transistor driver, or a FET driver. In our case, I've seen a lot of the forums are saying that they've got IGBTs in here. Our board had a FET in, and the circuitry here will explain that. So first of all, on the gate, well, let's start on the left. We've got this U3, which is this A3020. It's an optocoupled. You can see we've got an LED. I've just drawn a little bit of a block diagram in here. That's isolated, and it will drive this arrangement here. Funny enough, 2 NPN transistors. But it will be driven in a flip-flop type state. In other words, that one will be on and that one will be off, and it will flip, and so it will keep doing that. And why? Well, it's rather simple. Pin 8 is our VCC, so pin 8 up there. So that's our supply voltage. The supply voltage will go through to pin 6. If that transistor's on, it will go through this little 36 ohm 45 R45 36 ohm resistor and switch on the gate. But we know a FET is a voltage driven device. It has capacitance, so it's a charge driven device. So now this will charge up, it will switch on. The problem comes is when it has to switch off. So that transistor now will switch off. This charge is here, but where does it go? That transistor will now switch on. The charge will come down like that through that little transistor down there and go to pin 5, which is ground. The problem is we have a diode here, and we have a funny little bridge, and they've put this diode in here very simply put. When the voltage is switched on, so we're going through 8 through 6, we will have a high voltage here on the anode here. This voltage will be higher than the voltage that is here through that resistor and on the gate. We'll have a little bit of a voltage drop, this current limiting resistor for the gate of that FET. And then we have a volt drop again here. So this voltage will be higher than that voltage here. The transistor will be on. The FET will be on. When we switch it off, bang, that charge has got to go somewhere. So it will go through that diode, because the voltage drop across that diode is minimal and the resistance, so it will go through, down. It will help this resistor here and this resistor here to discharge to ground. So that's what that is doing there. Of course, we didn't check that diode and that IC, but we can suspect for sure, if we blew that FET, in other words, we blew that FET and we blew that diode down here, we can definitely suspect that that diode and that IC have gone. So let's check them, and I'll set some stuff up and we can come back. Right, so here we are back on the board. I've just connected some grabber clips. The red and black are on pin 2 and 3. We're going to drive that LED. The green and yellow are across pins 8 and 6, and I've just set my multimeter to continuity. I've got my bench power supply set to 1.9 volts, and I'm not going to limit the current. I'm going to switch the channel on. If this driver is working, well, that transistor should switch on, so we should get minimal resistance there, or a short. And 1.9 volts, nothing happens. But I can tell you we're putting 800 milliamps on the drive to that little LED in there. And to show you what I'm talking about, I'm going to just zoom in a lot on that, and I'm just going to put in, I'm just going to fix it. I'm just going to put some of this stuff on here. Now you should be able to see what happens with the current draw. There you go, you can start seeing it. The liquid that I put on there is starting to melt, or to evaporate, not melt. So yes, there you go. You can see that chip is getting very, very hot. I will just put a bit more on for you, in case you're wondering what I'm using. There you go. You can see the heat is causing the fluid to evaporate, and I'm not using anything fancy for that. I'm just using a lighter fluid. There you go. You can see nicely on the side of the chip. So that chip is indeed gone. It is toast. It's seen better days. And if I touch it, yes, it is rather warm. I'm just using lighter fluid to do that. Of course, I could have used isopropyl alcohol. The choice is yours. So definitely that chip has gone. So if we take our little clips out, obviously, if we zoom out, if that IC over there has gone, we need to be suspicious of these resistors and that diode. So when this failed, remember we said it failed short circuit. I can't remember, I think all the legs were shorted, so whatever power was there would be over here, so it would destroy everything. So that diode is definitely gone, and the way we can find that out is very easy. Let me just get my multimeter leads. these grabber clips are painful sometimes. Okay, so if we switch our multimeter to diode, very simply put, so all I'm going to do is I'm going to measure across the diode and dead short. So when these boards go, it's not enough just to have a look at the, if we take the board out the way, we have to look at the circuit. So it's not enough just to say, okay, that FET went and that freewheeling diode went. Obviously the circuitry around us went. So a good place to look as well is that diode and that IC. Beyond that IC, I'm not really worried, because if I can get the board back, from that IC down, we have a bit of circuitry down here. Here we have an LM324, a quad op amp, and here we have an LM329, which is a quad comparator. And then that goes off to our microcontroller unit. I don't suspect anything's gone down here. Simply put, because it would have, this chip is isolated. So yes, it managed to destroy our LED in there. That's not a major thing. That LED could have gone with time switching, whatever. So I think our damage ended here. So yes, we lost that transistor, that FET, we lost that common cathode freewheeling diode, and we lost that IC. I have checked these capacitors, even though I'm not really wary of them, just to see, because they're part of the switching circuit. And if we follow this a bit more, we've got MOVs down here, a little rectifier and little transformer for switching, and our switcher down here, and this is doing all the work to switch that transformer to give us our switch mode power supply. Obviously ISO optocouplers and things you can go through and check, but I don't suspect little voltage regulators and things like that. We really have to look at this main circuitry because of those blown fuses. Interesting enough, up here you can see that resistor that we talked about, that 33K resistor early on. That is just a current limiting resistor to limit the inrush for that capacitor. I wouldn't have used that, I would have used an NTC. So it's the first time I've negative temperature coefficient resistor to limit that inrush, but it's the first time I've seen that put in a fixed value resistor. I don't know why. Obviously there's some reasoning behind it, but yeah, maybe cost, I don't know. But anyway, I hope you learned something. So when you find that you're blowing these fuses, remember we worked from this side back, so we said, okay, well those fuses are blown, definitely we got a short. So we measured the output, we measured a short, and then we came to those two. So obviously it's a good reason, a good idea to check that freewheeling diode or discharge diode down there and that IC. And I suspect once we replace that diode and those two components, the FET and the common cathode freewheeling diodes, this board will be right as rain. Like I said, it's a DCMD, Delta Charlie Mike Delta 57 Papa. So let's finish up and we'll take it from there. And so we come to the end of another video. I thought it would be useful, instead of me just repairing the board and you never see what else could have been wrong, to show you what you should check. So it's always important to check the driving circuit for your FET, because if you've blown your FETs or your IGBTs, 9 times out of 10 you would have blown the driver for it as well. I will order the components and whatever. We'll come back and we'll do the soldering together, and then I'll make the schematic. I'll make a nice neat drawing of it with the actual parts that I'm using, because a lot of the original parts that were on this board you cannot find, so I had to find equivalents. So I'll put them on there with the original part marking and the new equivalent that I'm using, and we'll do the costing with that as well. As always, I hope you found this fun. I hope you found it enjoyable. I hope you found it useful. Take care, be safe, and we will catch you in the next one. Cheers.